Hello everyone. We're going to start the next chapter here with modeling with functions, and this one is trigonometric functions. It's going to take a couple of weeks. Pay attention, and we'll start off with something completely irrelevant. I was looking for heartbeat graphs and just happened to find a nice little graph. I think you can see it here up in the corner. There you go. There's the equation for the heart. Very nice. Anyway, with trig equations, I'm going to back up a little bit and say that this is part of a periodic function. So periodic function is one where there's a clear pattern of repetition in the graph, and it can go on indefinitely. So I thought a nice example of that was something like a heartbeat. So these are some examples here of heartbeats. And if you take a look here, you see that there's a repetition of the pattern. So these are 5 different graphs, 6 different graphs. So for example, if I take that second one, if I look here, how far do you go before it starts to repeat? So it goes up to here. Now I'm assuming here that the x-axis is time, and this one is like 1, 2, 3, 4, 5 of these big squares to get from the start to the part where it repeats. That's 0.2 seconds per square, I think, because it seems to say on the right hand side here that it's 60, which I assume means 60 beats per minute. So sorry, that's 0.2 of a minute. No, second. Anyway. But this distance here, from here to here, is the period. That's how long it takes, or how long along the x-axis that you have to go before it starts to repeat. And for future reference, because we'll get back to this, the period, of course, we use the letter, that's right, capital T for period. Why capital T? Because usually it's a time period, so capital T makes sense. Okay, so that repeats like that, and they're different for each one of these. So this one here, the period would be from here to more or less here. Yeah, that would be here, the period. So more on that later, but just to show you that there are graphs where it repeats, where there's regularity, and those are called periodic functions. The trig functions are part of that family. They're probably the biggest part of that family. All of these are kind of fancy versions of that. So, of course, I have a little bit of GeoGebra for you. So if I kind of get out of here and get over to the GeoGebra website here, I've created a little app that you can play with. There's a link in the lesson, and you can take a look at that, but there's a lot to unpack here. But I'll just show you first of all that what a sine function is. We've used sine before in just straight up trigonometry, right? But this one kind of records, so if I kind of back up, if you recall, we've used sine for things like, if I look at this triangle here, if I make the radius here 1 of this circle, and we're measuring from the center, the angle here is alpha, a little hard to see, but the sine of the angle would be equal to the opposite side over the hypotenuse. The hypotenuse in this case, I set it to be 1 because it's a unit circle. Unit meaning 1. So it's opposite over 1. So the opposite side, this blue thing here, represents the sine angle. So there's kind of a length associated with that. But really it's a ratio. It's this opposite side divided by the hypotenuse. And in this case, I set it to be 1. Okay, so I'll get back to that. But let's go back to our little interactive thing. What if we change the angle? What would happen to that side, that length there, that blue length? Well, the smaller the angle, the smaller that side would be. Now, if we kept track of that, that length would be on the y-axis of a graph, and the angle to which you rotate would be on the x-axis. That's what it would look like. A little bit of a spoiler there, but let's kind of flip back and take a look at that. So if I take a look at that, it kind of, see, the angle is almost 0 and the height here is 0. So the sine ratio is 0. And then it moves up and up and up, and it gets to be the same length as the radius. So that ratio would be 1, because it'd be those two lengths would be the same, the opposite side and the hypotenuse. The thing is, we can go beyond 90 degrees and kind of keep with that idea that it's simply that length here, the vertical length of this triangle on this circle. And you see that as the angle goes past 90 and towards 180 degrees, it goes down and down and down and down until you hit 0 again, and then you can just keep on going, except this time the length is negative, and it'll keep going more and more negative until it reaches a ratio of -1, and then on back. So that's why you end up with that kind of graph like this, where from 0 to 90 it's positive, and it gets increasing. From 90 to 180 it's decreasing, but still positive. From 180 to 270 degrees, negative, going all the way to -1. And then from 270 to 360, gradually, still negative, but going back to 0. And then the graph would continue. You can keep going past 360 degrees, it's just that it starts to repeat after. So the cycle repeats like that. Okay? For cosine, remember the cosine is the adjacent side over the hypotenuse, and that would look like that. So it's the length of that point there, and there'd be a little triangle, so really I should be drawing a little vertical line that joins it, but I didn't want to because I just want to make sure that you see that it's that length. So it starts, if it's the adjacent side over the hypotenuse, it starts off, they're the same length, so the ratio is 1, you know, and then it keeps decreasing that length until you get it to 0 at 90 degrees, and then it's negative, all the way to -1, and then decreases back to 0 from 180 to 270, and then from 270 to 360 gradually creeping in positives back up to that. That's all that the SL students need to know. Now I'm going to do a separate lesson, but just feel free to play with other ratios, such as the tangent, which has an interesting little graph there. And then even fancier are cosecant and secants and cotangents. And if you're wondering, where the heck are those lines coming from? This is the triangles that they're built upon. So the sine is right here, cosine, the tangent, the cotangent, the cosecant, the secant, and the cotangent. They're all there. What a mess. By the way, there's a little button at the bottom left-hand side. That's play, and it just kind of rotates through that. You can stop at any time. And if you look at the top right-hand corner, there's a little kind of reset button that you can press. There you go. And it resets the whole thing if you get too crazy. Again, HL, we're going to get back to this. You measure angles from 0 to 360 or higher, and you can work backwards into negative angles. That's not a problem. That's good for everybody. That's what normal people talk in angles. Degrees. Okay? It's the size of a degree has been set. It's arbitrary, but for pure mathematics, we don't like that. And for HL, you're going to have to measure also another way, which is a radian measure. More on that later, but if you just take a look, you'll notice that I'm keeping track of the circumference of the circle, or at least the arc of the circle as far as the angle is gone. So right now it's at 1.08, for example. what that is if you took that length and divided it by the radius of your circle, you would get that number. And so that ratio we use, oh, look, I hit one. That ratio we would use instead of using degrees. We would just describe it by how far you've traced out on this circle. And the reason for that is because a ratio has no units. So when we do applications, it's actually a lot easier not to use degrees. Anyway, I digress. So if we look at that, that's what the graph looks like. Notice from 0 to 90, positive for sine, 90 to 180, positive, and then 180 to 270, negative, 270 to 360, negative, and repeats. So the period of this function, which would be simply y equals sine x, like that, the period of this would be 360 degrees. By the way, for HL purposes, I've put in the radian measure also, 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, let's talk degrees though for now. So, what else do we have here? Oh, we got the cosine one also. So again, there's your little triangle. So it's the adjacent side divided by the hypotenuse. If we make that arbitrarily 1, that length would be exactly cosine, because it'd be cosine divided by 1. So cosine alpha would be equal to the adjacent side divided by the hypotenuse. So if the hypotenuse is 1, it's simply the adjacent side. That's arbitrary, I know, but that ratio would always stand true. And again, same deal. If you take a look at it from 0 to 90, it's positive, 90 to 180 negative, 180 to 270 negative, and 270 to 360 positive. Do remember what these graphs look like. Overall, if I chop this up into 4, a little quadrant like this, a circle like this, and so that any angle like this, the standard is we measure an angle in math counterclockwise. We turn counterclockwise and we establish the positive x-axis, this one, to be the 0 mark. That's arbitrary, and that's in math. If you did, for example, orienteering, you actually go from the true north and then you rotate clockwise to measure your bearings. So different applications, you may not always follow this, but this is the standard we follow. Okay? So this, for that triangle, this would be the adjacent side, this would be the opposite side, and this would be the hypotenuse on this. Except, usually on a triangle, we just stop at 90 degrees, but if you kind of redefine it like this, you can rotate all the way through, so you can have, for example, if I make a smaller version here, I can have an angle way over here, and this angle would be well over 180 degrees. Yet still you can form this little triangle like this. You can also think of this as an XY coordinate system here, and if you think of it that way, the x coordinate, okay, so remember the adjacent side is the x, the opposite side is the y value. So the x value would be equal to the adjacent side, right? So if you simply take the if you want that, it'd be just that x value there. The y would be the opposite side. Yeah. Okay. So in the case of a unit circle where the hypotenuse is 1, remember those are equal to adjacent would be cosine of the angle, and y would be the sine of the angle. Like that. Okay. So that's kind of cool. It's kind of interesting. Oh, very important here. if we're going to start working with angles again, always make sure that you are in degrees. If you're using radians, make sure you're in radians if you're measuring degrees. But if you're using sine, cosine, or even tangent, make sure you know that you're in degrees. And the way you do that is for Casio people, you just go to your normal home screen where you just do your normal calculations, which is your kind of this one here, run matrix. This one here, make sure you're in there, and then you'll be able to press, so that's number one here. Two, I want you to go to the setup. So this one. Okay, to get the setup, it'd be shift menu. Okay, then it'll take you here. Now make sure here you're in degrees. Okay, very important. You can measure angles in degrees, radians, gradients. Okay, degrees is what we're sticking with. Okay, so that's step 3. Easy. For the TI, what you do is you simply go to the mode button right here. Okay, and then it'll come up with this screen, and just make sure that you go here and you hover over that. You move your cursor over with the arrows and you press enter. Okay, if you do that, you're in degrees. If you pick up a calculator and you haven't used it for a while, good thing to check, especially before a test. Okay, now how do we use this thing? Well, we're going to be using the calculator. I'm sure you're surprised by that. If we take a look at from section 11A, questions from there in the SL textbook, they say solve the following equation. So if we just take a look at the first one here, this one, okay, what I do is I'm going to simply put in y1 on my calculator sine x, and in y2 cosine x, and see when they're equal to each other. So when they meet. Okay, without even going to the graph right away, remember, and you're going from 0 to 360, so from 0 to 360. Remember what sine looked like? So the first one looked like, so let's color code these. I'm gonna make that one red here. Look like this, right? Where this peaks out at 1, this peaks up at -1. And then the second one, okay, that's cosine, starts here, goes to 0, goes to -1, back to 0, and back to 1. So often you can kind of draw that fairly quickly like that. So where they're going to be equal to each other? Here and here. Where is that exactly? Well, let's find out. No spoilers. And yes, I know for some of you who have done this before, you're saying, hold on, I know some trig identities that I can solve this just a little more purely algebraically or without a calculator. I can show you that real quick. You do not have to do this right now. So what you do is, sorry, didn't want to do that. Let's just use x for the sake of simplicity here. Cosine x. What you can do is divide both sides by cosine x. And if you know a trig identity, this is equal to 1. That one you didn't need to know. But sine x over cosine x is tangent x. And you can actually solve that on your calculator by doing this. But there's a caveat. There is more than one solution. And if you do it like this on your calculator, this is the inverse symbol. For trig functions. Very confusing because you would think that's 1 over tangent, but I've mentioned that before when we use trigonometry. You only get one answer on your calculator, so you actually have to figure out that there's a second answer, and you have to use some fancy stuff to remember. I'll get back to that, but let's just stick to the calculator for now. So if you graph it out, like I said, you go to your menu, you go to graphing. I even forget what it's called. Let me just turn on mine here real quick. Yeah, just go on graph. Then you type those in. Make sure you press enter on the second and first in the second one. And then if you just go straight to draw, you may get this, which is bad because that's not the graph I'm looking for. Why is it looking so silly? Because if you take a look here, that's only 6 degrees. And you're also going into the negatives. Here, that's not what I'm looking for. If we go back to this, I'm looking for all the answers between 0 and 360 degrees. So I have to go to my window. So if you go Shift, Window, right there, okay, you'll get to this little thing, and I want you to set it. Think about it. Your X minimum, what did I say? 0. Maximum, 360 degrees. The scale really doesn't matter. Usually it's 1, but what it does, and I'll show you on the next screen, what this does is it kind of divides up your little kind of x-axis. Not a big deal if you don't mess with that ever. Dots also, don't mess with that. It just does a bunch of points on your graph instead of, it doesn't actually draw a line or a curve. The y values, remember, the minimum y value for sine or cosine is -1. And the maximum is 1. Now, instead of making it that super close, I just made it a little bigger on either end so I can see it nicely. Because then if I hit graph, so if I exit, so that's 1, then fix, so that's 2, and then you exit, and that's 3, and you can go back to just drawing this thing. You will get this, which will make you happy because it's really nice and it's clear. So I kind of buffered it a bit here with the extra 0.2 on either end here so I can see it clearly. So there you go. That's what they look like. And I'm looking for where they intersect here. So how do I do that? If you press, I think if you press exit, I forget, but you should see menu selection here, and we've done this before, but you use the intersection and it will give you an answer. I guess there's nothing really. It'll give you this one. So it tells you that it's when x is equal to 45 degrees. That's the first answer. It doesn't give you both at the same time. It gave you this one. How do I get to the next one? Press the side arrow. Okay. Once you do that, you get the second one right here. And that's when x is equal to 5 degrees. Very nice. I got both my answers. I can see clearly what's going on. I'm happy. I've got the 2 answers I'm looking for. If we go all the way back to the original question, sorry. This one they don't really say. They'll often say here solutions to let you know there's 2. Not always though.